In this wire, we have a long straight wire with a radius of almost 3 centimeters. It's got a current of 1.4 amps that's distributed uniformly over the cross section. At what distance from the axis of the wire is the magnitude of the magnetic field a maximum? So this is a lot like the coax problem, right? Without the outer conductor. And so we're going to turn again to Ampere's law. Right, and we just got to figure out the enclosed current. So, you know, if you have a wire, right, and here in this instance we are inside the wire. Right, because the radius of the wire is 2.757. Well, actually, we're asked where is the maximum. So there's the field inside and the field outside. Well, outside we know the answer, right? Outside's pretty straightforward because the magnetic field, because of the symmetry and everything, is a constant for any given r, and so the integral ends up being b onto 2 pi r. And once we're outside of the wire, it's all of the current is enclosed, right? So B is mu naught I over 2 pi r for r greater than equal to r, the radius of the wire. What happens inside the wire, right? This is all outside the wire. Inside the wire. Well, just like in the previous problem, we have to figure out what fraction is enclosed, right? So we take the ratio of the area enclosed divided by the total area, right, which just ends up being this. Okay, now that's the fraction enclosed, fraction of the current enclosed, and so very similar to the other part. Right? 2 pi r is mu naught. I enclosed now is I onto this fraction, right? So now we have everything we need here, and what we find is B is mu naught. B is mu naught I over 2 pi. Well, one of the r's cancels out, and we've got r squared over capital R squared. Oh, sorry, r over capital R squared. R over capital R squared. Right? And this is for r less than equal to capital R. So, when is this a maximum? Right? When is it a maximum? What happens, this, right? If you look at this one, inside the wire, it is monotonically increasing, right? Because it's proportional to the radius. It's monotonically increasing until r equals capital R, at which point we get mu naught I over 2 pi capital R. Well, if we look at this one, it is monotonically decreasing as r increases. So as we bring r down to capital R, we get B is mu naught I over 2 pi capital R. Well, fortunately, at that boundary, both of these equations give us exactly the same thing. We don't have a discontinuity in the magnetic field, right? A very important feature in physics is discontinuities are typically bad, right? Typically bad. And so what do we get for our answer for when is it a maximum, right? And at what distance? Well, at r equals the radius of the wire. R equals r, capital R. And that is the maximum point for it. Why? This is monotonically decreasing as r increases, so you have to come down to the minimum r that you can get. this is monotonically increasing as r increases, so you have to go up to the cat. The maximum r, and at both of those, right, at both of those, let's write it this way, B inner is mu naught I over 2 pi r, which equals B outer, which is also mu naught I over 2 pi r. And there you go.